I grabbed a marker.
So the question started from the field. So
yeah,
what is a field? What's the difference between the field and the particles, the electrons? And these particles that spring up from the fields, according to his question, do they just stay there forever? Like they just stay vibrating and showing up themselves up on these fields?
and we're going to talk a bit about how we, what a particle is. I think I've got a chapter on that now. But
A man-made construct.
no, it's a representation of the Poincare group.
Oh, man-made construct.
Sure. So are you?
Yes!
Uh,
Man and a
So
woman.
you can ask me.
yeah. Okay. So
That's
all right. Particles are quanta of a field theory. So I mean, there are two differences we could talk about here. I mean, the difference between quantum mechanics, which is the quantization of like a particle, and field theory, quantum field theory, which is the quantization of a field. Now, at a fundamental level, we're only talking about fields. Okay, an electron is a Dirac field, right? A quantized Dirac field. So, at the most basic level we describe, we have fields, we quantize them, which means that, we do either a path integral or we do a canonical quantization of the field, and the field and its conjugate momentum become operators. And from those operators, we construct a ground state. And we're going to go through this with several different fields, so you'll see how it works. But we construct a ground state, and then we construct quantum excitations of that ground state. And actually, each of those excitations might be thought of as a particle, or the whole superposition might be. But it is a quantum state of the field, of the relevant field, electromagnetic, or the Dirac field, electron field, whatever. Now, let me just see where we are for a minute here, because I'm going to talk about this in more detail very shortly. I just want to see. Okay, we talked about group theory. How far did we get with group theory?
I think we're about studying Spinors or something.
We're starting Spinors. Okay.
I think so.
Yeah, I see Spinors and the Dirac equation. Okay, did we do the complex representation for real three vectors? SSU2, right?
No.
So we haven't done that yet. Okay. All right.
I know you gave us one homework. I can't remember.
Yeah, if you read through, I think you'll find quite a few exercises actually. So all of the exercises in the chapters are assigned. I've spent some time actually blending these chapters back into the book. So what I may do is just post the whole book and tell you how far I've gotten with the editing. It keeps the chapter headings right and stuff. So let's see. Oh, you were getting off into renormalization and all sorts of things, I guess. But
Yeah, he was talking about the divergence in this
yeah,
QED.
yeah. Well, QED is quite manageable, and what you're saying is right. That you can show that there are two basic, distinct divergent integrals that come up when you're calculating QED transition amplitudes, and you can formally absorb those in a process called renormalization, which can be done several different ways, yielding the same results. But you absorb those infinities into your definition of the electron charging mass. So that what you say is, well, there's some bare mass such that when it's corrected by this infinite quantity, it's the mass we measure. So in place of this integral, you're basically putting in the measured mass and charge of the electron. It turns out that at higher order in perturbation theory, as you were saying, it's only these same infinities that occur. So you've actually taken care of all of those divergent quantities by this replacement. And then, of course, the proof is in the pudding, right? You make predictions of, say, ratios of cross sections and things, and they're correct. Right? So once you've made those replacements, now you can do calculations that are quite finite, and they make very precise predictions, in fact.
Can I ask you? But once you do the renormalization,
Yeah.
you have the mass of the electron incorporating the cloud around it, kind of, right? I mean, it's like you add all the other effects.
If you like the picture, sure.
Okay. But once you've done that, you can show that all terms, that it's a convergent series, if you keep doing that for every higher order, you can always renormalize and it'll converge to any number of any order.
Let's see. Is there a proof? I haven't seen a proof. I think that's the case.
Really? Okay.
Yeah, I think that when you have a renormalizable theory, that
I
the
don't understand the question quite.
well, okay, the contrast is with a non-renormalizable theory, where you find that at each order in perturbation theory, you get divergences that are distinct from the ones you've corrected at lowest order, and that's the case for general relativity. You don't have enough you don't have an infinite number of parameters that you would need to fix all the infinities in that. That's led some people to look at curvature squared actions for gravity and some alternative theories. It's not necessarily a strong motivation, but non-renormalizability is a problem for a quantum theory. The other thing that can be a problem, as you have in the strong interaction, is that the series just doesn't really converge. I know for the strong interaction, I'm not certain exactly the status for the electroweak, but the series is asymptotic. After a few terms in the perturbation theory, you're about as close as you're going to get, and it can actually diverge away after that if you keep doing perturbative corrections. The problem with strong, of course, is that the corrections aren't small. The coupling constant is of the order of 1 instead of 1 over 137. And so things do not converge well. The results, I know, in QED lead to predictions of a precise value for the fine structure constant. Now bear in mind that the fine structure constant is something that doesn't exist classically. It depends on Planck's constant. So, we're talking about measurements of something that is necessarily in the quantum realm. And the perturbative calculations have gone to 5th or 6th order in perturbation theory and predict 12 significant figures for the fine structure constant, and those agree with experiments that can also be done to that precision. So the predictive power, especially of QED, is extraordinary, much better than really any theory we've ever had before. When it comes to something like QCD, what people do is actually try to approximate the full path integral by taking a discrete limit of space-time. This isn't the model of space-time. What it is saying, okay, since I can't integrate over every path in a continuous space, let me build space out of lattice points, say a 6 by 6 by 6 by 6 space-time lattice, and set up some initial conditions at one corner and evolve on every path in the lattice, which is now some, well, at least countable number, and maybe not do things that loop too many times, but actually put it on a computer and sum over the phases over all the paths to make a prediction of a transition or something. That I know that masses, for example, are computed this way. Masses for quarks and mesons, the proton. I think they're getting better than 10% accuracy with that kind of lattice QCD, it's called, quantum chromodynamics. We probably won't do that this semester.
Are we going to do any QED?
Yeah, what I usually have as a goal for the first semester of quantum field theory is to get you to do a real QED calculation. You know, and hopefully we can move fast enough if you guys do all the exercises and turn them in like a week from Wednesday. How about? Let's see, you know, a stack of exercises from each of you. I should count up how many there are. But I was looking through and saw that the problem that I outlined last week it's one of the exercises in there already. So you'll find quite a number there. A lot of them are just small calculations to get you to use the notation and so on. But I do need to see some of those soon. So what I want to do next is first get you some understanding of spinors, and then look in particular at the Dirac equation. And we'll see, I'm not sure whether here or later we actually look at solutions to the Dirac equation. We definitely get to a number of its properties. But I think most of what we do in this chapter is to build the mechanism. So, that said, let's look at a simple example of spinors. There's your light.
Okay, we're good.
You good?
Yeah.
All right. A representation is a space for a linear representation, which is what we'll use a vector space on which a group acts. And if you know how a group acts on a certain space, you can generally write explicit forms for the group elements. That's especially true of a linear representation, where the things that act on vectors are matrices. So we end up writing the elements of the group as matrices. Well, we know that SO3, I think we looked at SO3. I meant to grab a better marker. Let's see if I have one here. Where we have some real 3x3 matrices, and we work through this, that act on real 3 vectors to give rotated real 3 vectors. Now, what I'm going to do is to write a different representation for this same thing. The property that constrains this transformation to be an element of SO3 is that if I look at the norm of x prime, it's the same as the norm of x. That's the property we know of this rotation. Now, the S tells us that we want these to be unit determinants. So we're not going to take x to minus x here. We'll leave parity as a separate discrete transformation. Now, given that this, and I'll call this x prime squared, and call that x squared, we're going to find now a complex representation, a two-dimensional complex space And that means that our matrices are going to be 2 by 2 complex matrices. We'll talk more about the two-dimensional complex space, but what we first want to establish is that we can, in this sort of a representation, we can actually implement this equality of lengths. Key to that is rewriting a 3-vector as a matrix. So what we're going to do is write a 2 by 2 complex matrix X as the real 3-vector dotted into the polymatrices, summed with the polymatrices. So sigma 1 puts an X here and here. Sigma 2 is I, Y, and minus I, Y here. And sigma 3 is a Z and minus Z there. It turns out that this is characterized by 2 properties. A matrix of this form is it's the most general traceless 2 by 2 you can write. Okay, let's just prove that. So let's let M be this matrix here, and suppose that M is Hermitian, so it's equal to its Hermitian conjugate. That means that alpha, beta, mu, nu is equal to alpha conjugate, beta conjugate down here, mu conjugate up there, and nu conjugate here. And looking at this equality, I see that alpha is equal to alpha complex conjugate, so that's got to be some real number, which I'll use Latin for. I'll try to use Greek for complex and Latin for real variables. The same is true of nu. Nu equals nu star is therefore real, so that's some real number. And then finally we have, let's see how to write that, beta. Oops. Beta has to be mu conjugate. And correspondingly, mu is beta conjugate. That's the same statement. So if we write beta as some a plus b I, no, let's write mu as a plus bi. Then beta will have to be a minus bi. Let's use c and d. Sorry, c plus di. Okay, so that means that a 2 by 2 Hermitian matrix, it always can be written in the form of a real number, a complex number, c plus di, and its conjugate, c minus di, and a second real number here. That's 4 real numbers to specify an Hermitian matrix. Now, we can, it's convenient to rewrite this A and B as, let's let A equal, let's see, how do I want to do this? All right, A plus B over 2 plus A minus B over 2. And I can write B as A plus B over 2 minus A minus B over 2, which seems a little arcane. But then if I rename these two, this is E and F, then this is E minus F. Now I can rewrite M as E plus F, E minus F, and C minus DI here, C plus DI there. And now we see that I can write it as E times the identity matrix, E here, then F times the third Pauli matrix. Then we have C times the first Pauli matrix, and we have D times the second Pauli matrix. Let's call this 2 and 1 and 2. All right, everybody see how the decomposition goes. So any 2 by 2 Hermitian matrix can be written as a linear combination of a multiple of the identity and some linear combination of the Pauli matrices. Now here, notice this is traceless, so the A is 0. So I can completely characterize a matrix of this form as being a linear combination of the Pauli matrices. Every traceless Hermitian matrix can be written in this form where these numbers are real. So 3 real numbers in the Pauli matrices, if and only if we have traceless Hermitian. Now, let's look at the determinant of that matrix X. Right, take the determinant, we get minus z squared, then minus the product of a complex number with its complex conjugate, x squared and y squared. So the product of these two will be x squared plus y squared, and we're subtracting because we're taking the determinant. That's minus the squared magnitude of the real 3 vector. So one way, a new way now, to describe a rotation is as any transformation that takes a traceless Hermitian matrix to another traceless Hermitian matrix. That guarantees that we're taking a real real triple of numbers to another real triple of numbers, traceless Hermitian, and preserves the determinant. So 3 properties we need. If we transform X, well, X transforms by some kind of a similarity transformation. So let's suppose we have something like this. What we need is X prime Hermitian whenever X is. We need X prime traceless whenever X is. And we need the determinant of X prime equal the determinant of X. Well, these aren't too hard to ensure. We can make the preserve hermeticity if we make a similarity transformation with the Hermitian conjugate. So if we take our transformation matrix acting on X, acting on T dagger, then X prime dagger is the same thing, reverse order dagger. So we get T dagger dagger, we get X dagger, and we get T dagger. 2 Hermitian adjoints bring you back to T. X is Hermitian, and T dagger is just T dagger, and that is X prime. So if X is Hermitian, as we used here, then X prime is Hermitian. Okay? Have you guys seen this before? You've seen this movie? Have you seen it?
I don't think I've seen it before, but I follow you.
Okay, all right. Well, and then we'll do the Lorentz group. Okay, so that accomplishes the first. Now, if we take the determinant of X prime, then we're going to get the determinant of T, determinant of X, determinant of T prime. The determinant of a product is the product of the determinants of T dagger. The determinant of the adjoint, the determinant of a transpose is the same as the determinant of a matrix. So what we're going to get here when we take the complex conjugate transpose is the conjugate of the determinant of T. So we get the absolute magnitude squared of the determinant of this matrix, transformation matrix, times determinant of X. So in order for the determinants of X to be the same under this transformation, we need the determinant of T to be
Positive
Plus
negative.
keep guessing.
0.
No, plus or minus 1.
Plus or minus 1.
It's complex.
Oh, so you can have
E to the I5.
this. Oh, you're doing that.
Any,
Okay.
right? Okay. Anything on the unit circle will have an absolute square of 1. Now, as it happens, if we look at this transformation, x prime is let's write t. Let t be some e to the I phi times, or let's say phi over 2 times t naught, where the determinant of t naught is 1. Okay, so that gives us an arbitrary phase in the determinant. Then let's look at the transformation. Then x prime is equal to e to the I phi over 2 t naught times x times e to the minus I phi over 2 times t naught dagger. But that determinant factor commutes with everything, just like we saw between the general linear group and the special linear group. That comes out and cancels, so the result of transforming by this general determinant e to the I phi matrix is the same as if we'd used one with unit determinant. The phase doesn't have an effect. So we want our group to act effectively, and so we can choose the determinant of our transformations to be 1. That guarantees that the determinant of x is equal to the determinant of x prime, and it restricts our group to unit determinant transformations. Okay, now the other property is that we need to delve into the transformation character of this just a little bit. Let's see here. What we would normally write for a transformation matrix is a similarity transformation. A similarity transformation usually takes the form of Tx T inverse. And what we actually need is Tx T dagger. So we, in order for a transformation of this matrix to be a similarity transformation, we need these transformations to be unitary. But any unitary matrix can be written as the exponential of an anti-Hermitian matrix. Any anti-Hermitian matrix can be written as I times an Hermitian matrix. So we can always write a relationship of this form for a unitary transformation, writing it in terms of an Hermitian matrix. Now, so easy to check. UU dagger is e to the I h, e to the minus I h dagger. So if h is Hermitian, this is e to the I h, e to the minus I h. And then multiplying out the Taylor series of these act like real regular numbers because the h's all commute with one another. And so this is then 1, and we see that u dagger equals u inverse. So u is Hermitian, or u is unitary if h is Hermitian. Now, in order to get unit determinant, det u equals 1. Right? There's another relationship, and let's take a minute to show this one. This relies on knowing certain properties of unitary and Hermitian matrices, and you may have picked this up from quantum mechanics or not, but in quantum mechanics we're always wanting to diagonalize Hermitian matrices. Our observables are Hermitian. We want to find the eigenvalues So we diagonalize them. The way we do that is to multiply by the unitary transformation made up of the eigenvectors. And it's transpose. And that will diagonalize a Hermitian matrix. Knowing that is the guideline to the proof that that's true. If you find the eigenvectors of an Hermitian matrix, then the matrix of those eigenvectors is unitary and will diagonalize H. But so knowing that I can always diagonalize an Hermitian matrix with a unitary transformation, let's suppose that U naught actually does that. So U naught inverse or dagger, it doesn't matter, let's let that be some diagonal form of H. So this is the matrix of eigenvalues of H, which are in general going to be real. If I carry out that transformation on the relationship between U and H, all right, this is the sum on n, 1 over n factorial, I to the n, H to the n. So I sandwich U naught and U naught inverse on this side. On this side, I don't worry about the sum so much. Each term has a U naught and a bunch of H's to n of them, and another U naught inverse. What I'm going to do in this product of H's is I'm going to insert identities in the form U naught inverse U. So between each pair of H's, I insert the identity, and now what I have is a sum on n, I to the n over n factorial, U naught H, U naught inverse to the n, which is now the sum I to the n over n factorial. This is diagonal. This is lambda 1, lambda 2, through lambda, I should use something besides n here. Let's be in capital N dimensions. How's that? Then that matrix to the nth power. But the powers of a diagonal matrix are just the powers of the eigenvalues. So what we end up with here are sums I to the n, lambda to the n over n factorial, m to 1, I to the n, lambda 2 to the n over n factorial, and so on down the diagonal. M to the n over n factorial. And now I can sum this term by term, and this is just the exponential of lambda I lambda 1, exponential I lambda 2, down to exponential of I lambda capital N. So now I have U naught U naught inverse equals a matrix that's the exponential of the eigenvalues, I times the eigenvalues of the Hermitian matrix. So now if I take the determinant of that, U naught U, U naught inverse, the cyclic property of determinants allows me, or well, just the product property. The determinant of U inverse is 1 over the determinant of U. So it's as if those two weren't there. So this is equal to the determinant of U, but it's also equal to the product of those diagonal values, which is I times the sum of, let's see, that's capital N, sum on little n of the lambda n. But now, one more fact, the sum of the eigenvalues of an Hermitian matrix is equal to the trace of D But the trace has a cyclic property too. Remember that D is just U naught H, U naught inverse, which is the trace of U naught inverse, U naught H, and this is 1, so this is equal to the trace of H. So finally, we have that the determinant of a unitary matrix is the exponential of I times the trace of the Hermitian matrix. I do wish I'd picked up some markers. Yes?
Okay, so if the trace is 0, you get 1.
If the trace, yes, right.
Right, that's the whole point.
So traceless Hermitian gives us determinant 1.
But here's my question. I've seen this before, and this was always a question.
Yeah.
What if the trace of H is 2 pi k?
2 pi k.
Then you still get 1.
That's true, yeah. Let's see, so what would that do? That would be... If I diagonalize a Hermitian matrix, I get eigenvalues here, real eigenvalues. Lambda n. And those aren't really arbitrary. I can rescale them, right? So if I have an eigenvalue equation, lambda k is lambda k, lambda k, then I can rescale the vectors, but these eigenvalues are characteristic. I can't add 2 pi n to this value and still have an eigenvector. So while this argument certainly, it's still going to have the same determinant if I change that that exponential form of h by 2 pi k on each thing, those are no longer the eigenvalues. So I've got a unique prescription for specifying this form. I guess that's the thing. This unit determinant doesn't depend on that, but the fact that the lambdas are the eigenvalues does.
So it's the eigenvalue characteristic.
Yeah.
That forces it to 0.
Yeah, if I diagonalize a Hermitian matrix, the diagonal elements are the real eigenvalues.
And you can't multiply those by 2 pi.
You can't rescale those. And certainly can't add anything to it. We don't need that overall phase factor. But in order to guarantee that a transformation takes a traceless Hermitian matrix to a traceless Hermitian matrix, we need for that transformation to be by a unitary determinant 1 matrix. What that means is that the group we're talking about is SU2. Right? That's exactly the 2 by 2 unitary matrices with unit determinant. So SU2 must be another way to accomplish the rotation group. Okay, so if we apply an element of SU2, so let's suppose U is an element of SU2, and if I write this matrix X is some X dot sigma, then I can construct X prime is U X U dagger. That's Hermitian. I know the determinant of U is 1, so the determinant of X prime is preserved. And the let's see. Do we need to prove that this will be traceless? If that's traceless, now I think that's immediate, because if I take the trace of X prime, then that's the trace of U X. Let's write it as U inverse. The cyclic property of the trace means I can cycle this one over to the front. So that's the trace of U inverse U X. And this is the identity. And so that's equal to the trace of X, which remains 0 under the transformation. So we've achieved our 3 criteria here by acting with a unitary transformation. So here's the curious thing. you might think that we've double counted because this transformation, consider minus u. If I let x double prime be minus u acting on x with minus u dagger, the minus sign goes away and I end up with ux u dagger, which is x prime. So I have two different ways to get to x prime. I can act with u or minus u. So it seems like we've got, okay, that clearly shows that we have two transformations that accomplish the same rotation of a real 3-vector. Now, that's actually a very real thing, because what we're acting on, this x, recall, is it's first and foremost, it's a matrix, okay? It's a linear combination of polymatrices. All right, the matrix under some kind of tensor transformation, notice it takes two transformation matrices to accomplish the transformation. That's what happens with a second-rank tensor. You guys know from relativity, if I've got a second-rank tensor and I want to do a Lorentz transformation of it, I do lambda AC, lambda BD, TCD. It's a bilinear transformation. Same thing here. All right, this X has two indices on it. It's a matrix. It's going to take two transformation matrices to transform it to the new basis. So we've changed from the linear representation of a 3-vector as a rank 1 tensor to a representation of a real 3-vector as a rank 2, albeit complex, tensor. That's what gives the 2-to-1 mapping between the spin representation and a vector representation. Okay, now I got off on the trace here. I wanted to emphasize how this works. We know by construction that if this X is traceless Hermitian, then the result of this transformation is traceless Hermitian. We also know that every traceless Hermitian matrix, of which X prime is now 1 necessarily, can be written as some real linear combination of the polymatrices. What that means is that going from X to X prime in a 1-to-1 way takes us from real 3-vector X to real 3-vector X prime, just by reading off the coefficients of the resulting thing here. So we can find how a real 3-vector transforms by acting in this bilinear way with elements of SU2. And I'm going to let you guys do that. Let me show you what I need to, let me look at what I need to tell you before I turn you loose on those problems. Yeah, I want to tune this representation of SU2 a little bit. We've said we can write Hermitian unitary matrices as exponentials of Hermitian. So if I have an element of SU2, I can write U as the exponential of some Hermitian matrix. And if I want unit determinant, then that'll happen if and only if the trace of H is 0. So H is traceless Hermitian. Well, we know how to write traceless Hermitian, right? It's some linear combination of the polymatrices. So I can write any element of SU2 as the exponential of I times the real 3-vector dotted into the polymatrices. Now, what turns out to be useful, and it's useful precisely because of this 2-to-1 mapping, right? When you apply two of these, you end up with double angle formulas. So I'm going to let this real 3 vector be phi over 2, some angle phi divided by 2 times a unit vector. And that gives me the way that I want to write any element of SU2, e to the I phi over 2, n hat dot sigma. So this is the representation that I want you to use in these problems. And then there are several exercises. I think I lay them out pretty clearly here.
That reminds me a lot of like, if you're trying to find a certain angle, there was a nice formula in quantum mechanics. You know, if you put everything in, and let's say they're spinning in this, you know, z direction or whatever,
Yeah.
and you want to find how they spin in some like n direction or something.
Yeah, you want to rotate a spin vector.
Yeah,
Right.
it reminds me
Well,
so much
yeah.
spookily like
A
that.
spin vector is a spinner.
Yeah.
Right? That's exactly what we're going to let these things act on.
Who would have thought things are related?
Who would have thought what?
Who would have thought things are related?
Yeah, right. Yes, really. They're not always, but
I don't.
yeah. Okay, so there are a couple of formulas. Okay, so I have an exercise here where I say let n equal 0, 0, 1. You know, I think I've rewritten this so I don't say that. I think this is. I think I'm looking at an older version here of these notes. Do it for a general n. Do a general n.
Oh, like ABC or something?
No, unit vector. You won't need to write it out in components. Well, or if you do, you just use n sub I. Right? This is just like what we did for SO3, right? I want you to derive that same formula, but by doing this. Right? So here's one of the calculations I want you to do, and I want you to do it for arbitrary n to let x prime equal, right, u x u dagger. So x prime is going to be equal to e to the I phi over 2 n dot sigma times, right, x we can write as some x dot sigma, and then the Hermitian conjugate, e to the minus I phi over 2 n dot sigma. And we know x prime can be written as some x prime dot sigma.
Now for those sigmas, do we have to take the complex conjugates of those two, since they're like one of the polymatrices?
They're Hermitian.
Okay.
The polymatrices are magical. They are Hermitian, they are unitary, they are everything. Okay, traceless, they're really very nice matrices. So because they're Hermitian, then the dagger goes away here, but you get it for the I.
Gotcha.
Right, you have to exponentiate an anti-Hermitian matrix to get a rotation. Right, so the I is accomplishing that. So carry this out, expand these exponentials. Well, I want you to do that in 2 steps, because, oh yeah, I have changed these notes. I'll post the current version that'll say just what I'm telling you now. But first, establish, so this is 2. 1, establish the identity that e to the I phi over 2 n dot sigma is equal to the identity times the cosine of phi over 2 plus I n dot sigma times the sine of phi over 2. So once you've established that, This problem is just multiplying Pauli matrices. And now, let's see, there's another order. Let's call this 3, call this 2, and never mind the inverted form here. Before all of that, the products of Pauli matrices of Pauli's prove that if I take one of the sigmas with another of the sigmas, if they're the same, I get and I get the identity matrix. So they square to the identity. If they're different, then I get I epsilon m n k sigma k. All right. So anytime you need to multiply out Pauli matrices, is when you exponentiate this, right, the Taylor series for this, and have to take powers of Pauli matrices, right? You know how to multiply Pauli matrices. So you can do it all with indices, and you know the dyadic notation might be helpful here too. But
So are those K's contracted there at the end? Or?
yeah, that's the sum.
Okay.
That's the sum.
I'm so used to seeing it as an up and down.
Yeah, it's Euclidean, so they're the same here. But yeah, sure. Let's put it up. Okay, so yeah, work these in reverse order. So work out the products of the Pauli matrices. Then work out the exponential of an arbitrary linear combination of the Pauli matrices. And then use that to find the transformation of x into x prime. And show that that transformation is the same one that we got for SO3. And now, this brings us to our spin up and spin down stuff. So let me move over here. I've said that our capital X here is a rank 2 tensor. So the question now is, what are the vectors, right? Well, so e to the I phi over 2 and sigma acts on something. Let's call it chi. Well, this is a 2 by 2 matrix. I can let chi be a pair of complex numbers. And then there's a perfectly well-defined operation of any element of SU2 on that two-dimensional complex vector. So the representation here is a complex two-dimensional vector space. These are called spinors. Now, a key to the 2-to-1 mapping, right? We found that there were 2 different unitary transformations that give us the same rotation over here. But if I look at u on chi and minus u on chi, right? Well, u on chi. Let's take a simple example. Well, here I'll do the one that is in the old version of the book. Let's let n be 0, 0, 1, so that we're exponentiating I phi over 2 sigma z. Well, that's easy because this is diagonal, and which means we just get e to the I phi over 2, e to the minus I phi over 2. So that exponentiation is trivial. Sigma z is diagonal, so we just get powers of plus and minus 1s. Is it clear? Question? We're okay. Okay. So if let's let that rotation around the z-axis act here, So I have e to the I phi over 2 e to the minus I phi over 2 on alpha and beta. And I get e to the I phi over 2. That could be any phase alpha, e to the minus I phi over 2 beta, some other phase. But, okay, here, clearly what I'm going to get is minus that. Phi over 2 alpha e to the minus I phi over 2 beta. And in general, those are not equal. Right? This is a different two component, two complex numbers than that. You can find values of things where they're the same, sure, but in general, those are two different complex numbers. So even though u and minus u both take x to the same x prime, u and minus u act differently on spinors. So we have some more fundamental object in the picture now. The rank 2 tensors are not the most fundamental objects. These complex 2 vectors are. And all of this hinges only on group theory. Right? We did not need quantum mechanics in order to do any of this. Right? The existence of spinors is a group theoretic property, not a quantum mechanical one. So it could well be that there would be macroscopic spinor states. Maybe there are, but what happens is that the property of spin is scaled by Planck's constant, and so it's very small, so we didn't really start seeing spin up and spin down states, direct representations of SU2, until we started measuring quantum mechanical things and looking in detail at atoms. But it wasn't precluded. In fact, when people started exploring ideas of supersymmetry, there have been a number of papers written presenting classical supersymmetric models that contain spinors and normal vector quantities, which, when you quantize those classical supersymmetric models, become supersymmetric quantum models. So you can do either first. You can go to spin and supersymmetry and quantize, or you can quantize and make it supersymmetric. Okay. So, everybody good on that? Now we're going to do the Lorentz. Just one small tweak of this whole thing.
Question.
Yes?
Should that be a minus in front of the E and the I phi at the bottom?
Where are we?
Right there where you pointed.
Here?
A little bit more up to the right.
Up.
Should that be a minus sign in front of that?
There's a minus here.
No, I mean in front of the whole. Because sigma z is 1 minus 1, right?
Let's check this. Okay, what this is the sum 1 over k factorial I phi over 2 to the k, sigma z to the k, which is equal to sum 1 on k factorial I phi over 2 to the k, and then this is always 1, this is minus 1 to the k. And now we bring all this inside, and we have the sum, I'll do it that way. We have the sum I phi over 2 to the k over k factorial, 0 to 0 here. Here we have the sum minus I phi over 2 to the k, bringing the minus 1 to the k in with the phase here over k factorial. And that is just, those are just the exponentials. So there's no overall sign here. We just have e to the I phi over 2, e to the minus I phi over 2. The minus sign in sigma z is gone here. So It didn't hurt to check, it's easy to slip up, but no, this was right. Okay, so to get the Lorentz group, we probably won't finish all this today, but there's one simple modification. It doesn't have to be traceless. So what we're going to do is let x be t plus z, x minus iy, x plus iy, and t minus z, which is clearly equal to x dagger. And now the determinant of x is going to be t squared minus z squared minus quantity x squared plus y squared is our invariant interval squared. Everybody see it? Yeah. So all we need to guarantee that we have a transformation that takes Hermitian to Hermitian while preserving the determinant. Now this is much easier. If I let x prime be any a times x times a dagger. Now let's see. Which way do I want to say this? Any a works here. All right, this combination is Hermitian for any a. But now, I need to preserve the determinant of x prime in order to preserve the line element. So this is going to be the determinant of a magnitude squared times x. There's no unitarity requirement here. That's the difference. So we need the determinant of a to be e to the I phi. Once again, e to the I phi, e to the minus I phi commutes with everything else and goes away. So the determinant doesn't actually carry out any transformation. So the group we want is the special linear group instead of unitary in two complex dimensions. SL2C is a complex representation of the Lorentz group. That acts on two component spinors, and we'll let's see. Well, we can actually use this very nicely to develop the. Oh yeah, I've rearranged a bunch of these things. We can develop the transformations of the Lorentz group this way. It turns out, well, let's see. Yeah, all right, got it. I'm actually looking at the wrong set of notes here, sorry. Let's choose a convenient basis. So, if I want generators for the Lorentz group, I can write a general. Do any of these things work? I keep switching off. I sort of recover for a little while and then fade. Any matrix here is going to do, but I want unit determinant. If I write this as the exponential of some matrix, then I need for the trace of that matrix to be 0. That'll give me determinant 1. And the way to write traceless matrices, one basis that I can choose like any 6 matrices. Tracelessness, notice, is 2 conditions in a complex space. So if I have alpha, beta, mu, nu, tracelessness replaces 2 of the degrees of freedom. So I have 6 degrees of freedom, and that's right for the Lorentz group. Now, I can write an arbitrary traceless 2 by 2 by taking linear combinations of the Pauli matrices, or I could take linear combinations of I times the Pauli matrices. And that guarantees that everything is traceless, and we've got 6 independent real numbers here. So we choose this as a basis. Let's let J be I times the Pauli matrices. And let's let K be just the Pauli matrices. Then these are infinitesimal generators for the Lorentz group in this SL2C representation. So real linear combinations, but the fact that we've got I times these makes each one complex. Is that clear? Yes? No? Not clear. Let's write it out. I want to write a general matrix of this form.
I get the traceless being a constraint.
Yeah.
It's that.
Yeah, that's what gives me unit determinant here.
Yeah.
Right. So if I write U dot sigma plus V dot I sigma, right? What is that? Well, that's some 2 by 2 matrix. Let's see. So for U, I get U3 minus U3. I get U1 minus I U2. I get U1 plus I U2. No, let's see. U1 minus I U2. Let me add these. And then I get something similar with V, but everything's times I. So I get I V3. I get I V1. Let's see. I times that is plus U V2. Down here I get I V1 minus I V2. And down here I get minus I V3. So putting these together I get U3 plus I V3, arbitrary complex number. Then down here I get, let's see, how do I want to do this? That wasn't right, that's minus. So here I get U1 minus V2 plus I U2 plus V1. That's some complex number. Up here, I'm going to get U1 plus V2 minus I U2 minus V1. And then down here, I get minus U3 minus I V3. So notice I get alpha and minus alpha here. So this is traceless. Otherwise, that's an arbitrary complex number. Now notice here I've got U1 minus V2, U1 plus V2. Those are independent. Right? Then here I've got U2 and V1 plus and minus. Those are 2 independent real numbers. So this is some A plus BI. This is some C minus DI. But then these guys are different. This is some E plus FI. And this is minus A plus BI. So I've got A, B, C, D, E, F, 6 real numbers to characterize a general traceless complex 2 by 2.
Mm-hmm.
Right? But what I've done is to parameterize it with the Pauli matrices. Because I know how to multiply these very easily. I can take powers of these very easily. I can work with these Pauli matrices very nicely. And in fact, I'm halfway done already, because my general A is going to be the exponential of I, say, U dot sigma for J, and then V dot sigma for K. And if I hold V0, I already know that those form SU2. Right? So a subgroup of the Lorentz group are the ones with V equals 0. Those are exactly the SU2 transformations.
Mm-hmm.
So the J's are basically giving me three-dimensional SO3, the 2-to-1 cover of SO3. Then the K's are going to give me the boosts. Right? Because I don't have I here, taking powers of this is going to cycle with positive numbers and give me sinh and cosh. And we can either work that out next time, or you guys can do it as an exercise for next time. But this will give us a very nice breakdown of Lorentz group. There's one more thing I want to mention. If we take certain combinations of these, let me get them right here. If I take L equal J plus K, and what did I call these? M times a half. And I take M to be a half J minus K. And all right, these are infinitesimal generators, right? We'd want to find the Lie algebra of these, and we'll work through the Lie algebra of these. These two actually commute with one another. Each gives a separate SU2. So the Lie algebra of SL2C breaks into two commuting copies of SU2. And this gives us pairs of conjugate spinors that transform oppositely. They're often written as something like chi A and chi bar A dot, where this transforms under L and that transforms under M, and L ignores this one and M ignores that one. You'll find this in Wald's relativity book. It's a very powerful technique for dealing with real quantities too. So we're going to get kicked out. Any questions? A few minutes maybe.
I have all the questions.
Okay, actually hit me with them at the beginning of class Wednesday. All right. So yeah, right. I mean, if we got 2 minutes, come ahead. But what do you have?
How many parameters are in the Lorentz group? There's 3 velocities, right? 3 boosts.
3 boosts and 3 rotations.
And then, okay, so 3 boosts.
All right, ordinary spatial rotations preserve the line element, right? Because they preserve just the spatial part. And then anything that mixes x and t, y and t, z and t. A boost in each of the 3 directions.
So each has 3 parameters.
Yeah. Good. All right.
If SO3 can be, represented as, SU2 over the complex plane, how come we can't just use SO3 and use the reals instead?
Because we wouldn't know how to act on spinors, and electrons are spinors.
Oh, couldn't you just make it into some larger tensor or something? No, because then you can
No.
multiply it. Because
No, you can't go the other way. Right? The SO3 does not know about spinors. Right? It doesn't know what to do with a spinor. And you can't write a real geometric, real space and represent spinors there. Try.
So they have to be over the complex plane.
Yeah. It's a 2-dimensional representation, but it's definitely complex.